Okay, so I'm going to get started. Today's announcements are you guys have your last recitation quiz in recitation this week. So like always, everything up through Friday of last week is fair game. This is just sort of a thing to make sure everyone's on track, keeping up with the material for the final. Also, if you submitted an exam regrade and didn't pick it up from me on Friday, I've given them back to the TAs so you can get it in recitation this week. Or if you can't make it, then email your TA. Also, the exam review is going to be here Friday, 9 to 11 a.m. I still need to set up lecture capture, but I'll hopefully get that done this morning. And then the final is Wednesday next week, 10:30 a.m. in Math 100. Okay. Any questions about this? Okay, cool. So I'm hoping to get through the last of Chapter 10 today, and then I'll set the sapling due date for like a week from now. Okay, so what we've covered so far in this chapter, we looked at making alcohols behave like alkyl halides by turning the OH, the hydroxyl, into a good leaving group. So that's like more or less familiar chemistry. We just have to tweak it a little bit to get it to where it can do SN2 or whatever. What we started looking at last lecture was a completely new set of stuff. And rather than looking at actual reactions just yet, we're looking at oxidations. So we started looking at how to look at formal oxidation level or oxidation state. Okay. So basically for each more electronegative atom or plus charge, we're going to add 1. For each less electronegative atom or minus charge, we're going to subtract 1. And for each equally electronegative atom, or radical, we're going to add 0. Okay, so we saw a few examples. You just go through and count like how many oxygens, which are more electronegative, just to put sort of a quick guide up here. Oxygen, nitrogen, halogens are all more electronegative. Less electronegative is mostly going to be hydrogen or any metal. There are a few other atoms that we could see here. I guess one other that's kind of good to know about is boron. Because that will sometimes come up as a question. And then equally electronegative atom, obviously, is just going to be carbon bonded to another carbon. I guess you can apply this more generally to any other atom. Like you could look at, does this nitrogen get oxidized or reduced? But at least like when we're looking at carbon, oxygen, nitrogen, halogens are all more electronegative than carbon. All of this stuff is less electronegative, and then carbon itself is equally electronegative with carbon, of course. Okay, so we looked at how to apply this to a few individual molecules, but where this is more useful is in looking at what changes on an atom during a reaction. So you can apply it over the course of a reaction and see, like, does something get more or less oxidized as this goes on. So we can take, like, CH4 and react it with whatever we need to react it with, in this case just O2, and we can convert it into CO2. So if we go through and look at the carbon, we could say, like, okay, this carbon has 4 bonds to less electronegative atoms, so it's 4 times -1 is -4 oxidation state, whereas over here, carbon has 4 bonds to more electronegative atoms, so 4 times 1 equals 4. So in this case, it's going up in oxidation state. which means this is a reduction for carbon. Okay, so usually carbon is the atom that we care about. If you went through and did this reaction from, say, the hydrogen's point of view, that might change. And if you went through and looked at it from oxygen's point of view, that might also change. As kind of a rule of thumb, well, actually, I'll get into that in a little bit here, looking at oxidizing and reducing agents. Let's do a couple more example reactions first. Okay, so if we take this thing, it's got 2 bonds to less electronegative atoms, so 2 times -1 plus 2 bonds to a more electronegative atom, which is oxygen, 2 times +1 gives us 0 in the starting material here. If we do whatever mystery reaction that converts it to, say, methanol here, that's going to give us 3 times -1 plus 1 times +1 for the oxygen that's still on there, or -2 overall. So this one is going down. So it's a reduction in the oxidation level. Oh, wait, sorry. I wrote reduction up here. That is completely incorrect. Sorry, that probably, yeah. I was like, something ain't right. Okay. Okay, so this is a reduction for carbon. Okay. Sorry for the confusion there. Okay, so any questions about those 2 examples so far? Okay, cool. So, where this gets a little more interesting is a lot of the reactions we've seen involve changes at more than 1 carbon. So, say we're looking at this molecule, and we react it with Br2, and as we saw in Chapter 5, this is going to involve adding a bromine to 1 carbon and a bromine to the other carbon of this molecule. So we can go through, figure out the oxidation level on each carbon that changes. We don't have to do the 3 methyl end carbons because nothing's happening there, so we don't have to do any calculations for them. So looking at this carbon, it's got 4 bonds to equally electronegative atoms. Its state is 0. This one has an oxidation state of -1. It's got 3 bonds to carbon and 1 bond to H that's not shown in there. After the reaction, though, this thing has an oxidation state of +1, and this thing has an oxidation state of 0. So all we have to do is add up the oxidation states of the atoms that are changing during the reaction. Here it's -1 total, and here it's +1 total. So this is an overall oxidation for the molecule. Okay. So any questions about that reaction happening? Basically just whatever changes during the reaction, go through and check that for each step. Okay. So why I'm bringing this up now is, you remember I sort of did that organizational thing at the end of Chapter 5 of like, hey, we covered a lot of mechanisms, but you can split them up into things that add this and things that add that and things that add this other thing. Let's take another look at that in the light of oxidation reduction chemistry. So for alkene additions, remember we saw the category of things that add 2 non-H groups. And at least for the reactions that we saw, all of the non-H groups were either a halogen or like an oxygen with something else on it. you'll notice that all of those groups are more electronegative than carbon. So everything in this category for alkene addition, at least out of the ones that we've seen, is an oxidation. So I did one of them up here, like dihalogenation. We're adding 2 bromines. We're oxidizing the molecule. What are some other examples we saw? We did this alkene with like halohydrin formation, Br2 and H2O. Notice that we're adding 2 more electronegative atoms onto the molecule, and the oxidation states are actually going to be identical to what they were in this example up here. It goes from 0 and -1 on this particular molecule to +1 and 0. You could also do it for haloether formation. The only difference is instead of an OH, you'd have like an OR of some kind, depending on what alcohol you used for that. Okay, the next category we saw was things that had 1 H and 1 non-H. So in other words, one carbon is getting a less electronegative atom, and the other carbon's getting a more electronegative atom. So this is not actually going to be a reduction or an oxidation. So they are called neither, for short, neither oxidation nor reduction. In other words, the molecule stays at the same oxidation level. So this is a pretty big category. It could be Markovnikov or anti-Markovnikov. I'll just draw a couple examples up here in the interests of time. So like this one, we hit it with HBr. You get a Br there, you get an H there. Just looking at this more substituted carbon got oxidized. It now has a more electronegative atom on there. And this less substituted carbon got reduced because now it has an extra H on there. So overall, this molecule is breaking even. It's getting some electron density back, but it's also losing some to the halogen. That would also be true for the anti-Markovnikov version of this with peroxides. I'm just switching which carbon gets what changes made to it. I'm not going to write every single one of these out, but I'll just do one more example. Say like, if we did BH3 or followed by aqueous peroxide here. This is hydroboration oxidation. So we're adding OH, anti-Markovnikov style, which still, if you look at it, 1 carbon got oxidized, 1 carbon got reduced, so it's neither overall. Okay, so questions about those examples so far? Okay, cool. And then the third category that we saw things that add 2 H's. This is going to be a reduction because we're gaining 2 less electronegative atoms. So we take this, we do hydrogenation, H2 and palladium on carbon. We're adding H and H, so both carbons got reduced, so this is a reduction overall. Okay, so how do we recognize whether a reduction or an oxidation or neither is likely to happen? We can sort of generalize reagents that oxidize by just writing O in square brackets on the arrow. So these are oxidizers. And we can do the same for things that reduce as H in square brackets, because these are the most common more and less electronegative atoms, respectively, that you would see on a carbon. So these are reducers, or reducing agents. Okay. So you could take this same alkene that we're working with right now and say, okay, square brackets O could give me a number of different things, all of which are in the same oxidation level. So I could get two BRs, I could get an OH and a BR, could get like a halo ether. All of those involve oxidations using some kind of oxidizing agent. Same thing for going the other direction. This with some kind of generic reducing agent on the arrow. The only reaction we've seen for that is hydrogenation right now. Okay, so I guess how do we look at a reagent that's on an arrow and like tell whether it's likely to be something that oxidizes or something that reduces? There's a few common trends that make it pretty easy to pick out. So typical oxidizing agents are usually going to have, obviously they have to have some high electronegativity atoms in there, usually bonded either to each other or to a central transition metal that's breaking the octet. So to some kind of central octet breaking atom that they can come off of relatively easily. So some examples that we've already seen a few times are things like Br2, H2O2, which if you look at the structure has two oxygens bonded together. CrO3 is another example, which looks like a chromium atom with 3 double bond O's coming off of it. Another example that we've seen is ozone, O3, which we know is going to also oxidize a molecule. I didn't draw that as one of the examples, but if you go through and draw like the starting end points of a ozonolysis reaction, you can see like this is oxidizing both carbon atoms that are involved. Okay. So reducing agents are kind of the opposite of this. Usually they're going to have a lot of low electronegativity atoms bonded either to each other or to a central low electronegativity atom. Okay, so examples that we've seen here already, or will see in the future, are H2, a couple of hydrogens bonded to each other, BH3. So all of these atoms are lower in electronegativity than carbon. So if you remember, we use this for hydroboration. Hydroboration itself, like this first step where we get H and boron on here, is actually a reduction, but then we bring in an oxidizing agent afterwards. And so the whole reaction overall ends up being like oxidizing wins. Okay, so BH3 is one, and then another that we saw like at the end of oxymercuration reduction. The second part of that name is kind of a dead giveaway that the reduction step needs a reducing agent. And if you remember, we used sodium borohydride for that. So that's sodium plus and a bunch of H's stuck to a negative boron. Okay, so one sort of throwback. If you remember, for ozonolysis, we saw two different workups for that. We didn't actually cover the names for what they are, but oxidative workup is one of them. That's the one that uses H2O2. Or it has the reductive workup, with DMS, which looks like this. So this is less oxidizing than hydrogen peroxide. And it'll actually, like the whole reaction is still oxidizing overall because of the ozone, but this one doesn't actually add extra oxygens on there. It doesn't oxidize further like hydrogen peroxide does. Okay, so questions about this kind of review in light of what we now know about oxidations? Okay, cool. So a little bit more stuff about oxidation from a not carbon point of view. So if carbon, the atom that we care about, is getting oxidized during the reaction, things have to balance out, so something else has to have gotten reduced. Okay, so a lot of transition metals that we're going to see here in the next few reactions can exist in multiple different oxidation states because they can violate the octet rule pretty hard if they need to. So many transition metals can have different oxidation states. And these are usually written with Roman numerals, if you'll remember from Gen Chem. Okay, so we calculate oxidation state for them the same way that we do for carbon. So like Cr here, chromium, we're going to see a lot of in this chapter. Here, chromium has 6 bonds to more electronegative atoms. So this atom in the middle here is chromium 6. We might also see later on osmium, which can actually do double bonds to 4 oxygen atoms at once. This is going to be osmium in the +8 oxidation state. So if we go into a reaction with chromium 6, and it turns it into, say, chromium 3, that means that chromium got reduced during the reaction. So whatever else changes during the reaction, which is hopefully going to be carbon that we're trying to change, carbon must have gotten oxidized. Okay. So a lot of the time, even if we have no idea like how to do an actual reaction, like if it's not one that we've covered in class so far, or if it's a new one that people are seeing in the lab and they're not real sure what's going on, they can at least narrow down what's happening just based on what's changing on the molecule, like oxidation, reduction, or neither. So for example, this reaction here, maybe there's a lot of stuff going on in your reaction and you're not sure like exactly which reagents are responsible for causing this change that happens to be going on in your flask. But then you can sit down and look at this and be like, okay, this carbon's getting reduced, this carbon's getting oxidized. This is a neither overall, it's neither oxidation nor reduction. So it's pretty unlikely that any oxidizing or reducing agents would be responsible for making this happen if they happen to be around at the time. And in fact, this one turns out to just be catalyzed by regular just acid. Okay, so it doesn't give us a huge amount of information, but it does at least help narrow down like exactly what might be causing this reaction. Okay. So any questions about this kind of big picture stuff before we go on to actually applying it to alcohols? Yeah.
For the hydroboration oxidation, you said it was overall an oxidation. How do we know that using the form oxidation? Which one?
So hydroboration oxidation overall. So we look at this carbon, it's getting reduced. So the hydroboration oxidation is overall neither, but well here, let me draw a little box in here so I have room to draw before I erase. So if you remember, the first step involves BH3, which gives us this with maybe some more complicated stuff on the boron depending on what else is going on. So this first step is actually a reduction because we're adding 2 less electronegative atoms. So BH3 is actually reducing it. But then we hit it with all the oxidizing stuff with a bunch of oxygens in there, including H2O2, which we know is an oxidizing agent. And that actually changes this one carbon out here from being attached to boron to being attached to oxygen. And so overall, this step is an oxidation, like this second part. And so it just so happens that overall, this molecule is kind of breaking even and ends up at the same oxidation state formally, even though it's gone through first a reduction and then an oxidation. So you would just want to draw out like the start and the end points of the reaction and see, okay, this carbon gets reduced, this one gets oxidized by the end of the thing. And so then you could figure out like overall start to finish it's doing this. But if you know like what intermediates it's going through, then you can pause it and say like, okay, hold on, at this midpoint, has it gotten oxidized or reduced so far? So you can sort of like look just at the 2 endpoints, or you can like stop partway in the middle and see what else is going on. Yeah, does that kind of, okay, cool. Good questions. Okay, anything else about this sort of oxidation reduction stuff before we get into details? All right, cool. I'm just going to erase the board if you guys want to take a minute. Okay. So, applying this oxidation reduction stuff back onto alcohol specifically, how is that going to look? Okay, so bringing this back into the topic of our chapter here. So pretty much all the reactions that we're going to be looking at for the time being, we're going to be starting with an OH on there, but we can actually look at this as like breaking it down by primary, secondary, or tertiary alcohols. So say we're looking at primary. If we take this and oxidize it a little bit, we can take this carbon from the 1 bond to oxygen, oxidation state, up to 2 bonds. And if we want, we can go up to 3 bonds. All right, so notice that the only changes we're making on the carbon is pulling off one H and adding 1 bond to O instead. So you go from 1 bond to oxygen, up to 2 bonds to oxygen, up to 3 bonds to oxygen, and we have to remove an H each time to make each of those steps happen. We can do the same for secondary, or at least we can start doing the same. So here's an alcohol. We oxidize, we pull off an H, and we get it to here. But that's pretty much all we can do if we're starting with secondary. We only have 1 H to get off of there, which means that we only have room for 1 more bond to oxygen before we run out of space. You might be asking, can I cut carbon-carbon bonds to squeeze another bond to O on there? And the answer is only under specific circumstances that we won't get into until later. So as far as we're concerned in this chapter, this is actually as far as we can go in oxidizing this thing. Okay, and so if we try starting with tertiary, we don't actually have any H's to pull off of there. We don't have any more room to squeeze any more CO bonds. So nothing's actually going to happen. Without cutting carbon-carbon bonds, which we won't do yet, we do not have room to squeeze any more O onto that carbon. Okay, so that's kind of a roadmap of what we're doing in this section. Then the question is, how do I actually choose like which of these reactions is going to happen? So we're going to break down the oxidizing agents in this section into 2 big categories. Okay, so I think the book describes them as strong or weak oxidizers. Stronger oxidizers are pretty much any version of chromium-6 in the presence of strong acid or water. Okay, so it's got to be chromium-6, but also you need some protic source around. And we'll explain why that is in a second here. So some real common examples that you might see are chromate, so like H2CrO4, which I think, yeah, that's the one I drew over there, is chromic acid. Or like a salt of this, where some of the H's have been replaced with, say, sodiums, like Na2CrO4 with, say, H2O and H2SO4. that has all the requirements met. It's got a chromium 6, it's got water and acid around. Or you could use something with multiple chromium atoms in there, so like dichromate. Which looks like kind of two of those things stuck together. I guess this one is technically dichromic acid, which is H2Cr2O7. 1, 2, 3, 4, 5, 6, 7. Yeah. Or again, one of the salts of this where the two H's have been replaced with sodiums. So like Na2Cr2O7 plus H2O, H2SO4, some kind of combo like that. Sometimes people won't actually bother writing the water explicitly because there is a little bit of water around in sulfuric acid or in whatever chromic or dichromic acid, just because that's how you get it into the aqueous form. So it could be like any combination of these, or it could be just straight CrO3, chromium trioxide, in H2O. That would also count. And another kind of different one is potassium permanganate, KMnO4, which is manganese here is a little bit different oxidation state from chromium. But it still does the same thing. The downside to this one is it works, but it also does some weird side reactions that will sometimes screw up other groups in your molecule, especially alkenes. So you might see especially older textbooks that use this one, but probably to be avoided if you can. Okay, so there's a whole bunch of different ways this could be written. Just look for the common factor of chromium plus 6. Or another way that it could be written is just Jones reagent. So you might see just the word Jones written on the arrow. So this is CrO3, H2SO4, and acetone, actually, which is mainly just there to solubilize whatever chemicals you're trying to work with so that they don't have to try going into the aqueous phase to get introduced to the chromium stuff. Okay, so a whole bunch of ways these could look on the arrow. But all of them have pretty much the same effect on your molecule. So these will all oxidize your alcohol as far as they can. So like in this sort of roadmap I have up here, they'll all go as far to the right as they can for that molecule. So if you start with a primary alcohol, something like this, they'll take that all the way to the carboxylic acid. If you start with a secondary, they'll stop at the 2 bonds to O state. So basically, they'll take every hydrogen off the carbon that has the oxygen and just wedge in as many other bonds to O as they can in there. Okay. So questions about that overall? Okay, cool. Just in the interest of time, I'm going to skip explaining why water makes a difference. Turns out it sort of helps the aldehyde that it makes partway like convert to something else, but that's not really super need to know info for the time being. If you're curious, it's in the notes though. Okay, so the other category that we're going to look at is weaker oxidizers. So these are chromium-6 that will dissolve without water. So you need a couple different special forms of chromium-6 for them to actually be soluble in something other than water. The most common one is PCC, which is short for pyridinium chlorochromate, which looks like and the pyridinium chlorochromate okay, so the pyridinium part might sound familiar to you, and that's because it has pyridine as part of the molecule. It's just got a plus charged pyridine, which is why it's pyridinium. And then it's got this fancy version of chromium with like a chlorine on there. Okay, so don't really have to be able to draw this, but you should recognize PCC as like a special weaker oxidizer. Another one is PDC, which does the same thing. I won't draw that out in the interest of time. Okay. So these things whole deal, and it's just these two in this category that we'll see, is they'll max out at 2 bonds to O. So even if you have a primary alcohol here, and it's hypothetically possible that with a stronger oxidizer, you would end up going to an acid. If you want to stop at the part-way stage, like stop in the middle where you've just got 2 bonds to oxygen, you can hit that with PCC, and that's all you actually need to write on the arrow. If you want, you can do a solvent. Typically DCM is what's used to avoid having water around. But that will get you to just 2 bonds to oxygen. I guess when I was learning this as an undergrad, I just remembered it as please create carbonyl, which may help. But yeah, it gets you to the carbonyl and then stops. It doesn't go past that part and put an extra oxygen on there. That also doesn't work for PDC, but PCC is kind of a lot more commonly used anyway. Okay, so the mechanism for all of these I probably won't go over, and I won't test on it on the exam, but it's actually kind of similar to the mechanism that we saw for, say, SOCl2 last lecture, where the oxygen bonds onto the central atom, in this case chromium, and then sort of a hydrogen gets pulled off from here, and it does almost an E2-like elimination instead of a substitution. Okay, so I'm going to skip thiol oxidation just because I want to wrap up this chapter today. I don't think I have time to do the synthesis practice right at the end of the notes, but I recommend, like there's no new material in there, but it's sort of putting together some of the stuff that we saw in this chapter. I recommend going through the synthesis problem at the end of the notes and just making sure you're familiar with how to like apply this stuff. Okay, so next lecture is our last lecture. I'm going to get through what I can of chapter 11, and then wherever I get up through, that'll be the cutoff for the exam. So, yeah? Sorry? Notebook? Or sapling? Oh, so I think I'm going to go through and trim out whatever problems I don't cover from the chapter 11 sapling.